Today?
Fine.
Fine. Better than yesterday? No? Well, it will improve after my lectures. Because after completing these 4 lecture course, you will have only easy exercises like machine learning, visual recognition, and so on. Just no math any longer. Anyway, let's start not with math, but with the question I asked you yesterday. Did anybody beat a casino?
No, we couldn't predict the outcome of the final game.
Well, this one is easier than the prediction of the yesterday's Euro final game. So I recall that the question was as follows. So assume we choose at random a number theta on the whole real line, so no restrictions on theta, and then a fair coin is tossed, and depending on the outcome, the number x is revealed, which could be either theta plus 10 or theta minus 10. Therefore, you obtain number x, and your task is to correctly guess the parameter of theta. Of course, given x, you know that theta could be either x minus 10 or x plus 10. And because the coin was fair, this happens with equal probabilities 1/2. So it seems that the best we could do is to correctly guess this theta with probability 1/2. Well, it turns out that probability comes at hand here, and you indeed can do better. Not very much, but still better, and believe me, even 1/100th, so 1/10 of percent is a big deal if you game continuously and many times. Well, again, I will not give you the whole details, but just give one extra step. So the idea is that one can randomly choose another real number. For instance, I ask our studio to randomly choose a number z from normal distribution. Okay. And this z has nothing to do with theta, of course, and with the coin toss, of course, because that doesn't know of existence of that coin. Therefore, z and x are independent, totally independent. And now, what do? We compare z and x. Okay, so either z will be larger than x or smaller than x. So the algorithm I suggest is that you should take theta to be x plus 10 in the first case, and theta to be x minus 10 in the second case. And I claim that this algorithm has probability of correctly guessing theta larger, strictly larger than 1/2. So try to justify this and then probably try to beat the casino. Anyway, so I will leave that to you as an exercise. And now we'll get back to our business. So that were my ambitious plans yesterday. Well, I still stick to them today. So yesterday we covered these two first topics. So we reviewed some basic notions of probability theory and then discussed parameter estimation problems, and already saw that it's not as easy as it could seem from first glance. Today we'll discuss the other two topics left, namely we'll try to test statistical hypotheses, and then discuss linear models, which we already saw yesterday during the Sergei's talk. And there will be lots of linear regressions modeled during this course anyway. Good. So, well, this is the plan for today's session. Probably I'll skip the discussion because we'll be discussing that anyway. Good. So I'll start with the following quote from Tom Huxley, which says that statistics is the only profession which demands the right to make mistakes 5% of the time. We'll try to clarify what is meant by what this means. So actually, yesterday we discussed parameter estimation problems, yes, and we usually started with the following phrase. So assume x1, x2, and so on are the data collected from some random variable with such and such distribution. For instance, it's the result of fair coin tosses. Okay, so this involves a parameter p, which is the probability of this coin showing the head. Okay, but in fact we are not sure that probability is equal to 1/2, especially when the coin is visibly distorted, yes, bent, so it's no longer clear that it should still land half of the times with heads and the other half with tails. Okay? So actually the first step should have been, let's check, let's verify that that's really the data from that given distribution. And even more, usually when we have lots of data, numerical data, say age distribution within some population, yes, then we say, okay, after normalizing, which means after subtracting sample mean and dividing by sample standard deviation, that is square root of the variance. Okay? These numbers become close or almost like data sampled from the standard normal distribution. Okay, but is this really true? Can we indeed, after such a normalization, assume that this is almost normal distribution and then apply all the properties of this distribution in order to derive such or such statements. Well, this leads us immediately to the problem of testing this assumption. And that's what hypothesis testing deals with. So hypothesis testing is a branch of statistics which try to verify statistical hypothesis. And any statistical hypothesis is just an assertion or conjecture about the distribution of random variables. Okay? So the task is to test such a hypothesis, which means that we would like to produce a rule or the procedure to decide whether or not this hypothesis is true. Well, actually there are much more examples in real life or in real science, empirical science, than we can imagine. Let's start with this example. That's the outcome of a real survey held in some large hospital, and the doctors tried to test the following hypothesis, that taking the aspirin, just usual aspirin tablets, will reduce the risk of a heart attack. Well, for this purpose, the following number of patients were tested, so they took part in the experiment. So almost 22,000 patients. Okay? And what did they do? They split this group in two, the testing group and control group. And in the second group, which is control group, the patients were given placebo pills, which means these were innocent pills which were sure not to affect the heart condition of that patient. And in the experimental group, the patients really took aspirin every other day or every day. And then they compared the number of ratios of heart attacks per 1,000 in the first and in the second group. And it turned out that in the first group, this ratio was considerably smaller than in the second one. Okay. Well, the question arises, is it really true? Can we indeed advise people who have poor heart condition to take aspirin as medicine to prevent heart attack? Well, certainly these numbers differ quite a lot, although the both groups are almost equal in size. However, is that really an indication that the aspirin helps in preventing the heart attack? Or is it just due to some blind random factors? Yes. I mean, blind chances. We saw yesterday that even if we flip a fair coin 100 times, then although the expected value of heads is 50, however, it's not quite random event that this number of heads will be outside the region between 45 and 55. Yes. So the difference is 5 for 100 tosses. Here we have 1,000 tosses, and the difference is around less than 10. Okay? So is it really important, or are these data significant? Do they indeed indicate that the hypothesis is correct? Okay. Here is another example from biology now. This is a very well-known Mendel's experiment on genetic experiment. While testing his genetic theory on dominant and dominant genes, yes, or alleles, he conducted the following experiment. He crossed this number of smooth and yellow tests with wrinkled green tests. And the outcome was as follows, that 315 tests turned out to be smooth and yellow. 108 were smooth and green, 102 wrinkled and yellow, and 31 wrinkled and green. Based on this, Mendel argued that two characteristics, namely the first of color to be yellow, between two characteristics of color, be yellow or green, yellow is dominant, and smooth piece also appear to be dominant, so this characteristic is dominant as compared to wrinkled piece. So based on this, he predicted that the combinations of these two characteristics have the following frequencies, probabilities: 9/16, 3/16, and so on. Okay, well, actually, these data observed differ from the expected value if the theory were true. Well, is this discrepancy big or not? Can we justify our theory, or Mendel's theory, based on these data, or do they, on the contrary, indicate that it should be rejected? Well, here it seems the results are quite close to the predicted ones, so probably there is no reason to reject the theory, and we'll stipulate on that later. Well, and we already tried tossing a coin 100 times, and already saw yesterday that the range between 45 and 45 and 55 is not as dominant, I would say, which means that quite often the number of heads, falls outside this region. So assume we tossed a coin 100 times and observed indeed not very typical number, 56 of heads. So does it mean that the coin is not fair? Or do these data support the hypothesis that the coin is fair? Well, these are range of questions which the statistical hypothesis testing theory is dealing with. So we'll start with reviewing the simplest approach, which is due to Neumann and Pearson. Again, what do we have? We have some data. These are usually numerical data, x1, x2, and xn, which were sampled from random variable with density n, which is not known for us. And based on these data, we formulate two hypotheses about f. The first is called a null hypothesis, which is conservative, meaning that it's not to be rejected unless we have enough evidence. This means that rejecting H0 falsely will lead to very serious consequences which we would like to avoid. So, when rejecting H0, we must be very, very sure in what we are doing. Okay? And we have a second hypothesis, which is an alternative hypothesis or just an alternative, which we accept if we have rejected H0. Very often this H1 is not very important. Okay? So, for instance, in the experiment with heart attack survey, what do you think would be the null hypothesis and the H1 and the alternative?
H0 is the hypothesis that the aspirin decreases the chance of heart attack.
It's helpful.
Yes, it's helpful.
Okay, so if we reject H0, what does it mean?
Could be increased chances or take no chances.
Just, yes, so it does matter probably. So there is no correlation between the heart condition and taking the aspirin. Okay, if we make a mistake in this if we have rejected H0, what does it mean? So again, H0 was that taking aspirin reduces heart attack chances. Okay, so we reject it. So we say that taking aspirin has nothing to do with heart condition. Okay. What if we have mistaken? This means that actually it helps, but we didn't detect it. Is it bad or not?
It's statistics, it does not have bad or not.
Well, probably there are many other medicines for, yes?
Sorry, but don't we take always H0 as no correlation?
Yes.
Wow, we are driving towards that. It depends actually.
Okay.
Here it's more clear, but actually in abstract setting it's not always clear what should be taken as H0. So let's change our mind and try to take H0 as the hypothesis that there is no correlation between taking aspirin and heart condition. Then if H0 is rejected, but it is true, what does it mean? We suggest patients to take aspirin and assure them that this really helps in preventing heart attacks. However, this is not true. Is it bad or not? Well, probably it's worse than in the previous situation, because the patient really believes this helps. However, in fact, it doesn't. So the price we play with is the life of this patient. Okay, so it's in fact a very serious thing and should be controlled. So maybe it's better to take this as a null hypothesis and try not to reject it unless we indeed have very clear evidence. Yeah? Well, there are many possible settings of this abstract scheme. For instance, we might wish to check the so-called goodness of fit. That is, we have some hypothetic distribution F0 and try to test that the density F from which these data were collected is indeed that F0. For instance, that's the case we started with. We can try to make sure that the data collected are normal. So they are taken from the normal distribution, say standard normal distribution. So then F0 is a standard normal distribution, and we try to check this hypothesis. And in this case, actually, the alternative is not so much important. We would like either to prove or disprove that our data fit the normal distribution. Or in the problem or in the model of, in the example with coin tossing, we want to check that the coin is fair, which means we know that F is some binomial distribution. We know the size of this distribution, it is n, say, and we know that there is some probability p behind this, because that's the probability that the coin shows up head. And we want to check that this p is equal to 1/2. And again, the alternative is not so much important. Well, these two examples are in fact a particular case of parametric families setting. So usually we have some parametric family of distributions, like binomial or normal, which depends on some parameter theta, which could be a single number as in the binomial distribution, or it could be two numbers. For normal family, we have mu as mean value or expectation, and sigma square as variance. Okay, and we set two hypotheses about this parameter theta. The first is that theta belongs to a subset theta 0. Say we would like to test the hypothesis that this p, probability of showing head, is in fact larger than 1/2. It might not be important to us to know the specific value of p, but just to detect that the chances of showing up heads have increased. Okay? Then this theta 0 would be the interval from 1/2 to 1, and the alternative would be 0 to 1/2. Well, of course, this goodness of fit also appears here if this set theta 0 consists of a single parameter value. So if we take theta 0, this set, to be single value, to contain only a 0.1/2, for instance, then of course this is the same as that one. Good. Well, we might have some hypotheses which specify this distribution F completely. For instance, this goodness of fit test specifies F to be F0, or if we want to check that the coin is fair, then we take just one particular case out of distribution of the binomial distribution family. Okay? So in this case, this hypothesis is called simple. Otherwise, hypothesis is composite. Good. So what can we do with this hypothesis? The only thing we have is our data, our numbers. So given these numbers, these data, in certain cases, we should consider them as supporting H0, and some of them should indicate that H0 is false. So we have to decide which data are in favor of H0 and which are contradict H0. How do we do this? Well, we just choose some subset of all possible data. So this is some region in Rn. Rn because we have n data and numbers, usually real numbers. So for a chosen subset C, which is called the critical region, we reject H0 as soon as our data fall in this critical region. And we accept H0 otherwise. Well, statisticians are crazy people. They are not satisfied unless they reject a null hypothesis. The reason for this is that then they are sure what they do. Okay? Therefore, usually, or very often, we say that in this second case, we do not accept H0, but rather we say that H0 is still not rejected. And probably then we'll try to use some other criterion and try to reject this H0, then we are done. Well, so that's what I just told you about. Good. So let's start again with this basic model example, the coin tossing. So we have a coin and want to check that it is fair. What can we do? So we repeat tossing it and observe how often it shows head. So we have our collection, our data. For instance, if we toss it 100 times and record each outcome as 0 or 1, depending on whether the coin shows tail or head. So head is a success, it's 1. Then certainly it's not so important in which what was the real sequence of zeros and ones. The order is not important. The only important thing is the total number of these ones. Okay? Well, actually that's due to the fact, and here the conditional probability comes in hand, that if we know that the total number of heads, say it is 56, then all outcomes that produce 56 trials have equal probabilities. So it doesn't matter actually which one we have. Therefore, the only important thing is the total number of these heads. This is our statistics t of x, which is the sum of these indicators. We sum once and have the total number of successes. Well, if the coin is fair, then the expected value is 50, of course, because we know that the corresponding random variable, which is the sum of these indicators, has a binomial distribution with p and n, and p is 1/2 hypothetically, and is 100. So the expected value is np, which is 50 here. So thus this critical region C should probably consist of all x's for which this statistics t of x, and that's the only meaningful statistics we could use in this case, for which these statistics, the value of these statistics differs from the expected one, 50. Okay, so we should reject the null hypothesis that the coin is fair if this difference is large in absolute value. But how large should it be in order that we are sure in rejecting H0? Well, yesterday we suggested that the range from 45 to 55 is a clear indication that the coin is fair. Okay. Let's play again with this file, our script. This. Oh, okay, it's the very first one. So here I recall we have numbers n, capital, and m. N is the number of tosses in one series. M is the number of repetitions. So, for instance, each of you have performed this experiment. So M is 50 or almost again 100, say. Well, and I just sample for each k between 1 and m. I sample 0 or 1 with equal probabilities. Oh, sorry, no, it's already. That will be the second. Okay. So equal probabilities, and let's look what it produces. So. Okay, so in these 100 repetitions, we observe the following outcomes. Well, there is as few as 37 heads in one experiment. Well, and as large as 16 heads. Well, there is a histogram, but it's not saying much more than what we have observed in this table. Actually, which is just that. The distribution is from 35 to 16. Okay. What else? Okay, we can calculate the number of non-typical experiments which produce the outcomes outside this range between 45 and 55. And in our case, it is 28. So it means in 28 cases out of 100, we got an estimate for P outside this predicted range. Okay. So what does it mean? Let's calculate the actual probability that in tossing coin 100 times we'll get the outcome between these two numbers, between 45 and 55. So I just sum the probabilities for binomial distribution. Okay, and so the outcome is 0.72. So we are very, very close in this case. The probability of hitting this interval is 0.72, and this means that with probability 0.28 we are outside this range. So we have a perfect match. This, but that's just our lucky case. Good. What does it mean? Well, actually, it means that if you want to reject our hypothesis that the coin is fair, upon observing 56 heads, 56 is outside this region, how often would we make a wrong conclusion? So, it means, let's take as H0 the assumption that the coin is fair. We toss it 100 times and got 56 heads. We want, upon seeing 56 heads, we want to reject this hypothesis. How often would we make a wrong conclusion?
20 out of 100.
Here, what it says to us, we got the number in the region, in the range between 45 to 55 with probability 0.72, which means the rest, that is 0.28, will be reserved to the cases where we got our result outside this region. So 56 is outside this accepting region, which means that 56 or other numbers outside this interval are occurring with probability 28. So if we want to reject our hypothesis, we will be correct only in 72 cases out of 100 on average, and in 28 cases out of 100 we'll give a wrong conclusion. Well, actually 28% is quite a big probability. It's almost 1/3. So if you say that, okay, here is the algorithm, but it only works 2/3 of times, in 2/3 cases of time. Yes, probably nobody would accept it as adequate. So we should reduce this ratio, this probability of guessing wrongly, or deriving wrong conclusion. Well, we can calculate, for instance, what should be the range outside of which this estimate p hat falls with probability less than 5%. 5% is typical, as we saw in interval testing, interval estimation yesterday. What is your guess? What is this interval outside of which this p hat falls with probability 5%. So from to
20 to 80.
oh 20 to 80.
Or 40 to 60.
Let's try 20 to 80. So here we are. 20 to 80. It's 1, which means that outside this region, this p hat falls with probability non-distinguishable from 0. So you of course are a very, very cautious person, but it's too much. So more moderate guess would be 26?
40 to 60.
40 to 60. Okay, let's try 40 to 60. To 60. You are correct. So it turns out that the rejection interval, or for this hypothesis, should contain the values less than 40 or greater than 60. Then we'll get wrong conclusion about our hypothesis only with probability 4%. It is less than 4%. Increasing, so including or excluding 40 and 60 from this, will already give probability larger than 5. Actually, this is actually related to the interval estimation we discussed yesterday. So we can give a 95% confidence interval for this probability, for this estimate p hat, which means that if p hat is within this interval, then p can be 1/2. So do you remember the interval estimation? These are two statistics, a of x and b of x, such that our parameter is in this interval with probability gamma. So in fact, if to have this probability p hat equal to 0.5, we should take the interval between 0.4 to 0.6, almost 6. So this is the confidence interval for our parameter p, which means that only if our p hat is outside this interval does it indicate that probably p is not equal to 1/2. Okay, so what we have seen is that by seeing 56 we cannot reject H0, because if we reject it, then we are wrong very, very often. Let's change our probabilities to 0.4 and 0.6. So now we again toss the coin and see the following outcome. So, there are extreme cases where there were only 46 heads, and another extreme value was 75. So 56 is somewhere here. It's not here, but there were 1, 2, 4, 5, so 10, 14.
16.
Okay, so 16 cases out of 100 where 56 was observed. So assume now we have two hypotheses. H0 is that the probability P is 1/2, and the alternative that the probability P is 0.6. And we observe, for instance, 56. Does it indicate that H0 is true or that H1 false? If we reject H0 on seeing 56, then we have estimated that the probability of guessing wrongly is almost 20 or 28%. However, if we accept H0, then it doesn't guarantee that it is correct. Because even if H1 holds, we can get this 56 or even less quite a lot of times. So it is not clear what does 56.2 do. Is it in support of H0 or of H1? As we have seen, we can have 56 quite often both under H0 and under H1. Well, we naturally come to the very important notion of errors. As we've seen, given X in the rejection in this critical region C, for instance, between 40 to 60, yes, there is still non-zero probability that by rejecting H0 we give a wrong conclusion just because we were not very lucky and got the result outside this acceptance region. We saw that there were 37, for instance, and 60 something in our simulation. In that cases, according to our most careful, cautious algorithm, yes, by accepting H0 even if the total number of heads is 40 or even 60, we still conclude, we still can get wrong conclusions. So this is a mistake, wrong conclusion. Another wrong conclusion is that X, even if X doesn't fall into this critical region, which means that according to our algorithm we cannot reject H0. Still H0 can be wrong because we saw that with 0.6 probability for P, it's quite often that the observation fall into that interval between 0.4 to 0.6. So this is again the case where we guess wrongly about the hypothesis. Accordingly, we introduce the notion of errors. There are errors of two types. The first, type 1 error and type 2 error. And the type 1 error is that H0 is rejected when it is true. So it's true, but we reject it just because x happened to fall into C. Or we can accept H0, that is, x does not belong to this critical region, but in fact H0 doesn't hold, H1 holds. Since H0 is conservative, the type 1 error is more important, which means that we should try to reduce it as far as possible. What does it mean that it is more serious? Let's give another example. The jury in a murder trial should take as H0 the claim that what? Yes, the person is innocent. Why? Well, there is presumption of innocence, yes. That is, no person can be held guilty unless strong evidence, and that's what we have in H0 hypothesis testing, yes. However, we can argue this as follows. What does it mean that, what does type 1 error means in this case? So H0 holds, but we reject it. So H0 is that the person is innocent, so it's acquitted, but in fact it is not. He is or she is not. Well, that's probably bad, okay, because that person could again be a serious threat to the society, but maybe not. Maybe that was just accidental misdoing. Okay, if we take as H0 the hypothesis that the person is guilty, what does type 1 error mean? So the person is guilty, but
We think she is innocent.
yes. So we are testing H0 as H0. No, sorry. Let's return to the first case and see what H1 mistake type error, type 2 error means in that case. So type 2 error means that the hypothesis is not rejected, it's accepted, but it's false. So what does it mean? Zero hypothesis was that the person is innocent. It is false, so the person is guilty. It is acquitted. However, some other person probably would be charged with that case, and therefore it's of course more serious. So a innocent person is convicted, and the true murderer is never caught. Then is more serious than the type 2 error that the murderer is acquitted. Because yes, please.
So, how could we say that type 1 error is more serious if, in case we could choose for hypothesis 0 different statements as you
Well,
before?
we choose between two possibilities. Yes. So my suggestion is that as H0 we should take the hypothesis that the accused person is innocent, because the type 1 error then means that H0 is rejected, although it's true. The person is innocent, but it's charged in this case. Okay? That means that the true murderer is never caught because it's never looked after, because everybody is convinced that that was the person. So it means that an innocent person is accused and the true murderer is free. And it's more serious than the situation with the type 2 error, because this means that the murderer is acquitted. Well, probably he'll never do any evil thing in the future anyway. So type 1 error here is more serious, because if we charge an innocent person, then in addition the true murderer is free.
So in this particular case, it is more serious, but generally H0 can be different.
Yes, that's true.
So it's generally.
Well, it depends on your interests. Well, let's consider the following situation. Some toy factory produces some toys, and we want to test if they are harmful to the children. So maybe they are made of toxic material, and they are quite dangerous for them. Then, depending on which side you are, you take as H0 different hypotheses. If you are a parent, then what is more serious to you? The most dangerous situation for you is that the toxic material is classified as harmless. So your child plays with that toys and probably suffers. That's more dangerous to you than the other situation where a harmless material is declared harmful. Because then you bear no cost. Okay? That's business of this manufacturer and not yours. You don't suffer in this case. However, if you are a representative of this company and you are very cynical, not you personally, cynical representative, you don't care about children, but only about your profit, then of course the situation which we have just discussed, when a non-toxic material is declared harmful, is very so to say bad for you, because you invested in this production, and then your toys are banned in the country, so you cannot sell them. Therefore, you just waste your money. You don't care much about the type 2 error in that case, which means that the material is indeed toxic, but you passed this test. Okay, so you don't suffer in this situation. That's the problem of the other side of this story. Good. Of course, if you are just tossing the coin, then well, who cares if it is 0.5 or 0.6. But in real cases, there is a difference. Okay. Well, so how do we choose this algorithm, this criterion, how to test our hypothesis? So because the type 1 error is more serious than the type 2 error, we should control this type 1 error. So we should fix an upper bound for the probability of getting this type 1 error. Say at the level of 0.5, so 5% or even 1% if the consequences of this type 1 error are very, very serious. Okay? And then try to choose C so that the type 2 error is minimized. Well, and this leads to the following definition. If the null hypothesis is simple, then the probability of the type 1 error is just the probability that your data false belongs to this rejection critical region theta under the condition that it holds. So theta 0 indicates that H0 holds, because that's your hypothesis. But you reject it because your observation belongs to this critical region. So according to the algorithm, you should reject your null hypothesis. Okay? So this probability is then called the size or the significance level of your test. And as said before, this size or significance level should be controlled from above at 5% or even small level. If, however, H0 is composite, then the size of this test is defined as the supremum or maximum value of the probability of type 1 error if theta runs through all admissible distributions in your null hypothesis. Okay, let's see how it works in real situations. Well, assume you have sample from the normal family with parameters mu at sigma square with known sigma square, and you want to test the hypothesis that mu is equal to mu 0 against the alternative that mu is actually larger. For instance, mu can be level of so I don't know the name. Toxic half toxicity, yes, probably toxicity level of this toy, and we want to make sure that it is at most mu 0, and our alternative is that it is in fact larger. So if we reject H, well, it's not the case actually. It's level probably vice versa. Mu 0 is the larger possible value of this thing. So we observe. Then what do we do? We observe that the sample mean x0 is the good estimate for the mean mu. Therefore, if h1 holds, then probably mean of x should take larger values, because it's an estimate for mu. If mu is larger, then probably we'll get larger x bar in most of the cases, which suggests that actually the critical region should be of the following form. So we reject h0 and accept h1 if the observed sample mean is too high, because this is probably the indication that the mean value is larger than mu0. Well, we should find now the appropriate constant c to make sure that the size or significance level of our criterion is given alpha, say 5%. To this end, we calculate the probability. This is a simple hypothesis because sigma is known and H0 specifies mu at level mu0, and therefore the size of the criterion is just this probability of the event that our observation belongs to this projection area, rejection domain for the given mu0. X belongs to C simply means that x bar, the mean of x, is larger than or equal than C, because that's the way we define our C. So we have to calculate this probability, and now we play the following trick. We just subtract mu0 from both sides and divide by sigma over square root of n. Why? Because this is a standard, this mu0 is the mean value of this random variable, and this denominator is the standard deviation, square root of the variance of this mean. After such normalization, what we have here is the random variable z, which has a standard normal distribution. This standard normal distribution doesn't depend on mu or sigma, because it has zero mean and variance equal to 1. So here we have known random variable with known distribution, and this z is just this fraction here. So we know that just from the definition, this probability is equal to 1 minus phi of z, where phi is the probability density cumulative distribution function for the standard normal distribution. Therefore, we want this to be alpha, and that means that phi of z should be 1 over alpha, yes, and therefore this z should be equal to the percentile of level 1 over alpha, or quantile of level 1 over alpha for normal distribution. So that's the point. What is this z alpha? Recall that for standard normal distribution, z1 minus alpha is the number such that the standard normal distribution has probability 1 minus alpha of taking smaller values, and therefore it takes larger values with probability 1 minus alpha. And that's the value for z we have here, because we want this probability to be alpha. Therefore, this number z should be taken as z of level quantile of level 1 over alpha. Which means that solving for c, we have the following expression for this number, and that's it. So under h0, the variable z, as we said, the standard normal distribution, therefore the critical region for this case is the following. So we should reject h0 as soon as mean value, the sample mean, is larger than this predicted value mu0 plus this expression. Well, this is actually called z-test because it's more conveniently written in terms of z statistics. We recall that this z variable, that random variable z, was taken to be this expression, and little z is just the value of this random variable. And therefore, using z notations, this critical region simply means that the standardized data, this statistic z, okay? So sample mean minus mu0 and normalized by the standard deviation takes value greater than this number. Why? Just because this little z is a realization of a random variable z capital, which has a standard normal distribution. Therefore, we know that values larger than this threshold only happens with probability alpha, because smaller values we get with probability 1 over alpha, therefore there is probability alpha of getting larger values. Therefore, indeed, our observations fall in this critical region with fixed probability alpha. Therefore, we control the probability that under H0 we derive a wrong conclusion. This wrong conclusion means that we get values in C, and this is equivalent to having the Z statistics taking values larger than that one, and we saw that this happens only with probability alpha. Well, if we have a left side alternative, that is, if the alternative is that the value of mu is smaller, then of course we can repeat the arguments, but the rejection region, the critical region, should contain all observation for which Z statistics takes small values. In this case, we compare them to quantile of level alpha percentile of the normal distribution. These two tests are one-tailed tests, so to say, because we only reject the hypothesis if Z is either large or small here. Or sometimes it's not important which alternative we take. We only test that mu is equal to mu0, and we don't care about the alternative. So in this case, the alternative is general. Okay? And what we then do, we do the same thing, but now we reject H0 if Z statistics is either too large or too small, and this produces the following tests. All these are t-tests, and there are similar. These were z-tests. Sorry, there is a similar t-test for testing the same null hypothesis in the case where the variance sigma is not known. The idea is we cannot use Z statistics any longer because it involves division by sigma, and sigma is not known. So a natural approach is to replace what is unknown by its estimate. So we replace sigma by sigma hat, which is the estimate. And we remember that the estimate for the variance is of this form. This is sum of squares divided over n minus 1. And so the only change is to take sigma hat instead of sigma. And if we do this, we get the following t statistics. And it's called t statistics because it is a sample from the corresponding t distribution, which is a student distribution with n minus 1 degrees of freedom. It's one of the standard distributions in statistics. We had this distribution yesterday. And for instance, two-sided t-tests, analogous to the previous one, is very similar. So we only have to write t statistics instead of z statistics and take quantiles of the student distributions rather than z distribution here. Okay, we'll play with this after the break.